Okay, so I like showing students a couple of titration curves before we get a lot into the details of the calculations, because you sort of get lost in the forest because you're looking at all the trees, and if you step back a little bit, it sometimes helps you get a better perspective. So there's actually two titration curves here, one in red and one in blue, and one represents a weak acid whose pKa is 5, and another one represents a strong acid, and the molarity and the volume, right, of titrant and the molarity and the volume of the acid, it's 0.100 molar, and I forgot to put on its volume, it's 10 milliliters. And the molarity of the titrant is 0.100 molar. And we're assuming monoprotic acid being titrated with something like sodium hydroxide as a strong base. Okay, so typically the titrant is a strong base for a weak acid titration. And so what we see is a couple of different things that are different about these curves. You notice the blue one is at a lower pH. This is pH and this is volume. And the red one is at a higher pH. And so you can sort of surmise, just based on the fact that there's a weak acid and a strong acid, that the weak acid is the one in red, simply because it's at a higher pH, which means it's less acidic. The other thing that you should notice is that as you titrate, right, when you get the volume of titrant to 10 milliliters, right, it's going to have 1 millimole of acid in the solution and 1 millimole of base. And what you should notice is that's the what we call the equivalence point, the point at which the moles of acid and moles of base are the same. So equivalence point, moles of HA equal moles of NaOH added. I like to say it that way so it keeps clear that that's the titrant, the thing going in from the burette. So you'll notice the volume's exactly the same. That's because when you're titrating, you're not measuring the strength of the acid. What you're actually doing is measuring the moles of the acid. And since they both have the same molarity, they're both going to get to the equivalence point at the same time. Now, you're familiar with the term endpoint, right? And we call the endpoint because that's when you stop titrating. The endpoint is where you see the color change, and it's related to the indicator and its color change. So when you saw that phenolphthalein turn pink, that was the endpoint of that titration. And one of the things to recognize is it turns out the endpoint and the equivalence point are not always the same, and most of the times, in fact, they aren't the same, but they usually are close to each other if the indicator is properly selected. So phenolphthalein turns pink at about pH 9, which is actually up here. And the equivalence point is very close to that value, but it's not exactly that value. The titration for the weak acid, the equivalence point and the end point are a little bit different. Turns out for most acids, though, those two values are relatively the same. I could zoom in maybe a little bit, but you really can't see. You see, this is just past this line. But that's on a scale that you couldn't measure on a burette. It's a very, very small value, okay, difference. So we have endpoint and equivalence point. Both are about the point where moles of acid are equal to the moles of base added. We have the pH of the weaker acid being higher, but you'll notice something that up here, they both have the same pH curve. So, and that's because this pH is just determined by excess strong base. And another way to think about it is you've completely burned up all the acid. It's a limiting reactant problem. There's no acid left in the solution. And so really what you're doing is from this point here on, you're just diluting this strong base because you're putting it in, but there's no reaction to use it up. And so basically the pH goes up the same for both the weak acid and the strong acid, a little bit past the equivalence point. Another thing to note is this volume here. 5 milliliters is 1/2 of 10. 10 is where my equivalence point is. This volume at half equivalence point, so I'm going to call it the half equivalence point volume, has this really mystic name called the midpoint. All right, it's not that mystic. It's just the middle, right? And for weak acids, there's an unusual property that shows up most of the time. If you look at where that crosses, right, it's almost exactly at pH 5. This line here represents 4, and I think if I go to laser, it zooms back out. Yeah, this is 4 and this is 6, right? So this is crossing almost exactly at 5. And what you'll notice for most weak acids is the pH at midpoint is equal to its pKa. So these are some of the things we'll be looking at, all these values I'm talking about during the course of this first part of the chapter.